I thought we would just have a short video to show another form of the chain rule. Now, the way you used the chain rule on the last video problems, that's the way you're going to do the chain rule most of the time. But we're going to be getting to something in the next chapter that, if you put the chain rule in a slightly different form, is going to be easier to use. So let's see if we can go back to the same problem that I worked on before. When we developed this form of the chain rule, we just said, here's a composite function, and to take the derivative of it, the main function is x cubed, so the derivative is 3x squared, but instead of x, we put in g of x, this other function, x squared minus 1, and then we multiply by its derivative and get 2x. Perfectly good way of doing it. If we go over to here, and instead of calling this x squared minus 1, instead of calling it g of x, I'm just going to call it some other letter, like u. So u is just x squared minus 1. If I know a u is that, I can take the derivative of u with respect to x and find out that it's just 2x. Notice that's 2x. And if we rewrite this as y equals u cubed, now if you just look at this, can we take the derivative of y with respect to the variable u? Well, it's not x cubed, it's u cubed. So instead of the derivative being 3x squared, it's going to be 3u squared. And since u itself is really x squared minus 1, what do we notice? That dy du is equal to this. And notice that that is the same thing as here. So what can we say? We can say that f prime of x, which is dy dx, is really equal to dy du times 2x, which is du dx. So more in a Leibniz type notation, this is the chain rule in a second form. So I'm going to kind of skip ahead quite a bit in the course to an application where this might show up, just so you get some feeling about it. So don't worry too much that I'm trying to teach this new application, but just to give you an idea where this can be useful. And this is where we really get into some applications of calculus. What if we had a circle and we knew something about that circle? It was increasing in size, such that the radius of the circle was given by that expression, where t is time and r is the radius. So as time was getting bigger, the radius was getting bigger. Well, as the radius gets bigger, the area of the circle gets bigger. So say you wanted to know the rate at which that area is getting bigger with respect to time. The trouble is, the only variable in a circle that we think about is the radius. And we know that the area is a function of the radius. It's pi r squared. But we don't want to know the rate of change of the area with respect to the radius. we want to know with respect to time. As time is changing, we want to know how fast the area is changing. So we don't want to know dA dr, we want to know dA dt. But we don't have a as a function of t, so we can't just use our regular formula. But we can go up to here and say dA dt is dA with respect to what we would like to do. So instead of putting a u, I would really like to take dA dr, because I know what that is. It's pi times 2r. That was pretty easy to do. So I want to go dA dr and then multiply by, we're calling this r, so dr dt. That is the other form of the chain rule. So we know dA dr is 2 pi r, and we can get dr dt. The rate of change of the radius with respect to time is 3t squared plus 2. And then we've got a formula for the rate of change of the area with respect to time. So if you knew what the time happened to be, you could just put that in for t, and with that value of t you could find r, and you'd have solved the problem you were trying to do. So here you're seeing some real calculus. This is a few weeks from now that you'll have to be doing this. But I think it's just good to show you this. There is another form of doing the chain rule and why it would be valuable in the future. You probably won't use it too much right now. So, thank you.